our recording and see where we're at and review a little bit what happened last time, okay? Yesterday, I held an office hour. I got a good about 10 or 11 or 12 students join online and I recorded on YouTube. Feel free to take a look at it. We went through the exam number 1, the sample exam posted on Canvas. We also answered some questions about detailing the concrete cover and everything else on that. So as we stand, the exam will have 4 problems. So there will be, first one will be a short answer, multiple choices. And the second problem and the third and fourth will be calculation problems. That means fully solved problems, right? And I can tell right now, one problem will be doubly reinforced section. Doubly reinforced section, that means have compressive reinforcement in it. And that will be in terms of analysis. That will be in terms of analysis. Another problem will be in terms of singularly reinforced section design without given geometry. Okay, so the third problem will be singly reinforced section design without given geometry. All right, that means no dimension will be given. Now, of course, the width of the section might be given, but you start from somewhere, right? You have to go iteratively find out the height and depth and so on and so forth, and also reinforcement. Okay, and just to be clear that whenever you see a concrete cover question, you are required to use the calculation method described in the lectures to do the calculation for B min, for B minimum. All right. I mean, table A5, it's okay to use, but when you use table A5, be mindful some of the criteria for table A5 have to be met. Sorry, so some of the criteria to use table A5 have to be met before you use table A5. Now, the best practice I find is you do 2 calculations. One is using your hand calculation by the lectures, and then compare the number with table A5, just get a ballpark check. So you won't be far off, okay? So that's another detail about it. So that's the 3 problems. The last problem, the number 4, will be an irregular section. Irregular section, that means either it's gonna be a rectangular section with opening, an I or T-beam with an opening in it, or it will be a T-beam design, okay? So for irregular section, if it were for irregular section, you're only responsible to find out the design moment, that is phi and n. So that is more of like analysis problem, all right? It's more of analysis problem. But for the T-beam, you are responsible for the design. That means you have to find a geometry first, the B effective, remember the BE equal to BW plus 2BF, right? Have to use the right equation to find the width of the section and find out the design for it. Okay, we have the notes for that, so that's that. All right, so total 4 problems and the items you can bring to the exam. You're able to bring a letter size, not printable size A4, front and back, both sides, okay, front and back. You can put everything you want on it. You can write something on it, you can print and glue to it, doesn't matter, whatever you want to do on the crib sheet. All right, and scientific calculator, basic calculators are needed, all right, are needed. So just plus and minus and multiply and divide, that's it. Okay, so that's the calculator. And last but not least, you are allowed to bring ACI code 318 with you. You're allowed to bring ACI code 318 with you. Okay, like I mentioned last time, we'll roughly have at least 1 proctor. If time allows, I'll have 2 proctor be there, proctoring exam. Made the exam in such a way that there won't be so many problems. But if you have any issues, you can raise your hand to the proctors. They know how to handle that. Okay, I have given them instructions. They know how to handle that. Okay, now the exam will be 2 hours, so really prepare yourself. I have put together and I'll rerun it today and tomorrow to make sure the exam are made, no errors. So I think it took me about half an hour to round the number out. So I think for you, 2 hours is more than enough time. But then again, I would urge you to do a lot of practice before the exam, okay? And some of the students asking me, what kind of materials do I need to prepare for the exam? Do you have additional materials? The answer is no, I really don't have additional materials. The materials I have are notes, the ones that we do in lectures, and homework. And when I say homework, especially number 3. And for the homework number 3, the graders are really working hard on them. They will return to you during or before the spring recess. So you have a whole week before the exam happen on the 24th. Okay, and now last but not least, if during the study, if you have any questions, feel free to email me or schedule a time to meet me and we can discuss. If there are so many questions accumulated, we'll do another office hour next Tuesday. If not, we will see you guys in the exam on 24th. Okay, all right. So with that, questions on the exam. Any questions about it? Anything covered? Anyone? Folks, are we ready for it? All right, well, I hope you're ready, okay? I hope you're ready. All right, so without further ado, let's go back to our business, right? Or teaching the shear design part today, okay? Shear design part of the quick review, what we have learned so far. So from previously, the lecture notes, right? We have covered why we might have diagonal crack in the beam. Why we might have crack in the beam, and that is critical, right? So the reason is that we have a stress distribution in the beams, and at different locations, the principal stress directions are different. The principal stress directions are different. So based on that, we might have 45-degree cracks, right? 45-degree cracks, and the presence of the 45-degree cracks demand us to have reinforcement in the vertical direction, and that is what we need for stirrups. Okay, the reinforcement in vertical direction, that's what we need for stirrups. Okay, so you can see that basically after we get the stirrups and longitudinal reinforcements assembled up, you have reinforcement cage, right? Reinforcement cage like that. So that was the gist of the last lecture. Okay, so if previously we have the theory, and today we're going to show you how to mathematically calculate it, So today we're going to get into the calculation part or equation part, okay? So today we're going to talk about the shear design, okay, and mechanism and design code, okay? Mechanism and design code. All right, so let's review, right? What we have done is that we have checked the diagonal crack in the beam, right? So there has to be some 45-degree cracks in the beam due to shear. And let's use the example we showed last time. Say we have a uniformly distributed load on a simply supported beam. Excuse me. And then just say that I have a 45-degree crack, right? And to make it more precisely, and let's just say that the 45-degree crack cracked right here, near the support, not quite on the support, but near the support. All right. And now I give you a little bit preempt information here. Just say that it's roughly, it's going to be depth D away, depth D away. Okay, and just say ds, okay, that is the depth of the bars, and I have longitudinal bars right here, don't forget. Okay, so I have depth ds away location for this diagonal crack. I'll explain to you later, next lecture, actually, why we assume ds away. But let's just say that that's where my diagonal cracks are at. And I can cut the section like we do the free body diagram, remember? In the statics and mechanics materials, we do free body diagram, right? So we can just cut it like that. So I use a dashed line, red, to connect with this continuous line and to finish this cut. Okay, once I've done this cut, I basically separate this beam into two parts, right? So make a cut and separate the beam into two parts. The left side looks like this. Of course, I have the support right here, but I have a crack like this, right? A more of 45-degree inclination, and then end here with a straight line. Okay, so that is the cut look like. All right, and through this cut, I exposed the several things. First of all, I now exposed this portion, right? This portion, okay, and I call this the compression portion of the cut because that is on the top. Right, so I will naturally have a compression force going this way, and now that compression force naturally will shed a shear force as well, and let's just call it VCY. And the reason why I call it VCY with an arrowhead is that VC is the concrete shear resistance, Y meaning the vertical direction. Okay, meaning the vertical direction. Still, this is my y-axis, and this is my x-axis. Okay, so that is called VCY. All right, now, once I made the cut, and you notice that the second portion of the cut is this nice, beautiful curved section, right? Curved section. And I say that along the 45-degree angle, I can draw an effective shear force, and let's just call it VA here. Okay, VA here. And the reason why I call it VA, because VA represent aggregates. A represent aggregates. And the reason why I say aggregates is because if I can zoom in here to see what kind of interaction I have on this inclined portion of the cut, is that if I zoom in and use a magnifying glass, I see that what's really happening is that at the cut, if you take a look at the concrete, right, it's not smooth. It's not smooth. Or more precisely, you will have some aggregates, okay, like this, and that bites into the aggregates from the other side of the cut. Okay, it is actually the aggregates bearing and friction caused this shear resistance. Okay, caused this shear resistance, and hence we call it V aggregate. So this A here represent aggregates. Okay, and to be precise, we call it aggregate interlock. Okay, aggregate interlock. So that is where the shear contribution is on this inclined portion of the cut, inclined portion of the cut. So again, naturally, when I make this cut, not only I expose this vertical section, expose this inclined, a little bit curvilinear section, but also I expose my reinforcement. I expose my reinforcement, right? That is my bars underneath right here, right? Although it is a bar, it is only in the tensile direction, right? But it does have a cross section. So whenever you have a cross section, naturally, I will also have a shear resistance on the bar. And let me just call it VD. All right, let me just call it VD. And you may wonder, what does the D mean? The D, subscript D means here, dowel action. Dowel action. Okay, so that's the three shear components we have when I make the cut. When I make the cut. All right. So what does it really mean? What does it really mean when you make the cut, Bob? That means that if I can do this, the total shear contribution and the total shear contribution from the, and I say this is from the concrete side of it. Okay, you said, Bob, yeah, from concrete, so you can call it VC, but what happened to VD? D naturally from the reinforcement. Yes, but you got to figure where does D coming from, right? So when you try to do the shear, the bar was fixed inside the concrete, isn't it? So it is still the concrete that hold on to the bar that provided that shear resistance on the dowel action in the form of dowel action. Okay, so these three components consist of the total shear resistance for concrete, total shear contribution of concrete. So that is VC equal to VA, aggregate interlock, VCY, shear resistance in the compressive zone, and plus the dowel action. Dowel action. Okay, so I want to name these terminology, right? So VC is the concrete shear resistance, total concrete shear resistance, and VA is called aggregate interlock. So shear resistance from aggregate interlock. So shear resistance from aggregate interlock. And if you're smart, and I think you are, you realize that this is just going to be a short answer problem to exam number 2, right? So this is shear from aggregate interlock. All right, now VD will be the shear resistance from dowel action. So VD shear resistance from dowel action. Okay, so now there you have it, right? And last but not least, VCY is the shear resistance from the compressive zone, from remaining actually, because when I do the 45-degree cut, there's only a small piece of diagonal, small piece of a compressive zone left, so remaining compressive zone. All right, so that, ladies and gentlemen, are the shear contributions for the design, All right, so you see, this is the cut without any stirrups, isn't it? Without any stirrups means that in this section, all you see are the longitudinal bars, What if I now provide a shear bars, right? Shear reinforcement stirrups. So let's say that, let me use a different color. The shear resistance, and use a purple color here, come from the stirrups and the stirrups actually are looking like this. Okay, and miraculously, just say that I have one stirrups poking through this cut. Okay, miraculously, somewhere, some reason, I have one stirrups poking through the cut, and the rest stirrup just sit like this, nicely, evenly distributed. In this case, okay, not always the case, but in this case, it assumes nice, evenly distributed. And I have a top bar to hand the stirrups, to place the stirrups on the top. Okay, so that's my entire reinforcement case. Now, within this, I will have the hanger bar here as well. Okay, but note that since it's only a hanger bar in compression, so we do not have dowel action on top bar. We do not have dowel action on top bar. So the shear resistance from the top hanger bar were neglected. Okay, there were no shear resistance from top bar, right, in compression. But now, since I exposed a stirrups, okay, I exposed the stirrups, I would anticipate there would be some shear resistance from the stirrups as well, right? So let me call it VS. Okay, let's call it VS. So VS will be the shear resistance, shear resistance from stirrups. Okay, from stirrups. Okay. All right. So now with all these terminology, okay, you start to figure out, okay, so the shear resistance from stirrups has to be in terms of the tensile stress in the stirrups because it is along the line of stirrups, isn't it? So VS, which is also in the vertical direction, should equal to A, and be careful, folks. Now we typically use AS, the area of reinforcement, area of steel for flexure, right? We use AS, but for shear, we use AV. Okay, so this is the area of reinforcement, for stirrups. Okay, for stirrups. Okay, let me zoom in a little bit so you can see better. And now that is area, and we assume that the stirrups also yielded. And be careful, folks, we are not using Fy anymore for stirrups. We have used Fyt. And the reason is that the yield strength of stirrups is a little bit different from the yield strength of the longitudinal bars, which we will talk about it later, okay? So this is yield strength of stirrups. All right, okay. So with all this, right, with all this, I have put everything together now. I put everything together now. Okay, so now with all this, I can say that the total shear resistance, Vn, okay, remember this? This is called nominal shear resistance, nominal shear strength or shear resistance. I like the word resistance, okay? Shear resistance or shear strength. You see from the textbook and others call it shear strength. It's the same thing, okay? Same thing. Now Vn should equal to Vc, which is the concrete part. Let me do a division line here so you won't muddy the water. So Vc is from the concrete and plus Vs. Right, naturally, right? So the total shear resistance of the section comes from both the resistance of the concrete and the resistance of the stirrups. Okay, so now this is the nominal shear resistance, right? If I were to do design, so the design equation for shear becomes different, right? For shear is a little bit different, right? So now I have phi, and don't forget, this is also the strength reduction factor. But this is a stress reduction factor for shear. Okay, this is stress reduction factor for shear. And know that, okay, know that phi for shear always equal to 0.75. Means it will not change. Remember in the flexure design, phi is a function of epsilon t, but for shear, phi is always 0.75. Okay, and that is in the ACI code. That is in ACI code. Okay, and precisely in the ACI code, this is ACI 22.5.1.1. Okay, so with that, I say, okay, look, phi Vn, that is strength reduction multiplied the nominal shear strength, has to be greater than and equal to V U, which is applied shear load. Okay, and then, ladies and gentlemen, you can find this same place in ACI 22.5.1.1. Okay, all right. So now that is a shear equation. That is a shear equation. Okay, so now you have all these, right? Let me go ahead and call it equation 1 and equation 2. So normally when we have the equation, you would do in the shear analysis is that you find out VC first, you find out VS, add them together, you get a VBN, and find out VU. Okay, that's a normal process will look like to you, right? Based on these equations. However, in our business, we normally have the concrete section sized up, not based on shear, but based on flexure. Okay, so I would say normally VC is restricted. Okay, normally VC is restricted. So the business is to find VS. Why to find VS? It's because once we find VS, and then we can determine the stirrups. How much stirrups we put into the section. Okay, so that is the process we normally do for reinforced concrete design for shear. So with that, I say, okay, if I want to follow this logic, if I want to find out VS, then I cannot use the equation 1 or 2 straight. I have to use an alternative equation, right? Alternative equation. The alternative equation is VS, then the shear resistance from the steel has to be greater than or equal to VU divided by phi minus VC. Minus VC. All right. So now you have seen this, right? Now you say, okay, look, now I understand. So step number one would be find VC. And step number 2, use VU, VC to find VS. And step number 3, since VS is a function of the area of reinforcement for stirrups, so I can find stirrups reinforcement area. And then that will conclude the design process for shear. Okay, so that would be the logic sequence, right? So if you know this logic sequence, let's follow it. The first step would be how to find VC. And that is when we say that VC is a shear resistance from the concrete, and we mentioned that usually it's given in terms of section size. That means that I already know it's width B, and I already know it's height H, and on top of that, I should know the depth DS as well. Okay, depth DS as well. Okay, with all this given information, how do I find VC? Okay, now in this scenario, ACI says, look, you can find VC several ways mathematically, right? You can build a nice model to find it, but in our approach, ACI says, look, we're going to do empirical equation, right? So empirical approach to find VC, okay, is preferred. So what the empirical approach looks like in ACI, there's actually a test has been done. Okay, you don't see the data, but there has been a test done on ACI. So in a test, they tested thousands of beams, actually precise 2,000 beams, more than that. They normalize the data, they test all of them, right? Just pure concrete, okay? And we listed the shear resistance VC normalized by the width of B, and then versus the horizontal axis to be the compressive strength of the concrete prime C, and the depth of the beam DS, okay? Okay? And now you have a lot of data, right? You have about thousands of data, something like that. All right, and once you have the data, you do a regression analysis, you fit a line through the data. And through this fitting, you actually find out there's a relationship between VC and prime C and the geometry B and DS. So this equation through data fitting is actually VC equal to 2 lambda, and don't worry, I'll explain what lambda is. square root of F prime C, compressive strength of the concrete, and B, and now this B is not any B, it's called BW. BW, and explain why it's called BW, okay? We must by ds, the depth of the section. All right, so that is the equation, and you should be able to find this from ACI table in the ACI 318 code table 22.5.5.1. Okay, 22.5.5.1. All right, so that is an empirical equation to determine a shear resistance for a pure concrete section, right? Pure concrete section alone, the 2 lambda square root of prime C BW ds. Now, let's take a look at the parameters. So lambda is a density parameter, okay? So that is 1.0 for normal weight concrete. So what is normal weight concrete, Bob, you ask? Well, normal weight concrete meaning concrete I gave you without saying it's otherwise, right? If I don't say anything, it is normal weight concrete. Just normal concrete, right? And actually what's really means is that the aggregates in these concrete are solid, not porous. All right, so there are two things in concrete, we know that, right? Binder and aggregates. For normal weight concrete, aggregates actually in terms of solid. There's no holes, no pores in it. All right, but if I say it's a lightweight concrete, that means you have sand aggregates, right? Sandy aggregates means the aggregates might be porous. Okay, so in case of a porous aggregates, you have lightweight concrete. You have lightweight concrete. And now for lightweight concrete, lambda equal to 0.75. A deduction, right? Has to be a lower strength. Has to be a lower strength. Now that's for lambda. How about BW? Bob, BW is what? Well, BW is the width, right? But BW also is the smallest width that can cut across the section. Smallest width can cut across the section. So give you an example, what do you mean by smallest width? Now, if I have a T-beam, BW is the web width. BW is the width of the web. Now, if I have a rectangular beam, BW should equal to a width of the rectangular section, right? Just BW equal to B. But if I have a box section, box beam, this usually happens in the bridge structures because the box have higher rigidity in plane because it has a larger torsion resistance. Never mind. Now I have a box beam and let's just use a cross to indicate the opening in the middle. So for this, BW is actually this width plus this width. So this is half BW and this is half BW. Okay, so that means actually if you look at all this, the definition means if I cut the narrowest section of the beam or of the structure, and that is BW. Okay, so that is the principle. So now you have it. Let me ask you a question, and I will pick my victim, so be careful, right? I pick my victim, so be careful, okay? So say if I am going crazy, I say, I want to do a S&T type of beam, so I do a S like this for artistic reason, right? I do an S like this. Okay, S like this. Okay, and now what would be my BW? What would be my BW? And before I do anything, let me tell you that this S has a uniform width of T across this drawing here, across this pattern here. Okay, so think for a second, what would be the BW for this section, right? And also, if this is the case, I also want to do S and T, right? T, you know that, so I don't want to do T now, right? How about I do a mining, right? I do a minors, right? So M, again, the M, my M looks like this, right? Pretty ugly, but I'm trying my best here. So I just say this is my M here. Okay, and let's call it T. Okay, and to make it more funny or interesting, and this is not an M anymore, right? Looks a little bit weird, but just say that there's an opening here in the middle. Oops, fancy that. Okay. Okay, so this is opening in the middle, and this is T again. This is T again, and this is T again. I know the drawing doesn't really do its justice, but let's just say that I made S and T, and what will be the BW for this case? Okay. All right, so now I'm going to pick my two victims, victims to answer the questions. And these are really challenging. So no right answer, wrong answer. Okay, just spit out whatever you think they are. Okay, so let me find the first victim. Jessica. Jessica, are you there?
Yes, good morning.
How are you doing?
I'm good. How are you?
Not too bad. Beautiful weather today, right? So let's take a look at the first case. What is BW for an S section here?
Would that be 3T?
Well, think of it. Yeah, that's a good and interesting answer, right? But think of it, right? The definition of BW is, let me just write down here and give you a few seconds to think about it. This is like the smallest or the width of the how to phrase this, width of the narrowest part of the section. Okay. So that means imagine I have a blue line, horizontal line, start scanning, right? Start scanning. What would be the smallest section along these scans?
So it would just be T then, or it would just.
There you go. That is absolutely correct. All right. Well, thank you, Jessica. That's the right answer. Okay, smallest. Okay, so that is the T. All right, so not 3T, not 2T, but the narrowest. All right. Now, second problem. Now, know that, right? What would be the answer for the second problem? This weird M shape. And by the way, thank you, Jessica, again. And let me find my next victim. Matthew, Jason.
Hello.
Hey, how are you doing, man?
I'm good. How are you?
Not too bad. So now Jessica has answered correctly for this one. How about you give a shot for the second one, right? What would be the BW in this case?
So the narrowest section would go across the bottom, right?
Well, think of it, right? That's correct. And what would be the number now, right?
Is that 3T?
That's 3T, exactly. So BW equal to 3T. Good answer. Thank you. So now, ladies and gentlemen, you see that, right? So it has to be the narrowest section. Okay. All right. So now you know, right? So let me spit out some things for you, exam number 2, and make sure you can circle back and look at it when you prepare exam number 2, right? So if I have a beam like this, let's just say that I have a beam like this, I-beam, the BW always going to be in the web, right? But if I have a irregular section, like we mentioned last time, when I have opening, and unfortunately, if I have to do opening in the middle, which is a big no-no, but just in case, I have to stuff a duct there to get my water through it, right? So the BW will be the narrowest, right? So if the opening has a width of B opening, okay, so BW would have to equal to the original BW. Let's just call it BW prime, so BW minus B open. And use that as your BW, okay? Always has to be the narrowest section, okay? Good. All right, so that is the definition of BW ds. Well, it's the easy part, right? ds is just simply the depth of the beam. And note that it's not dt, it is ds. So this is the depth of the beam. And when I put the notation mark here, ds means this is to the centroid of the group of the bars, centroid of group of the bars. Okay, folks, group of the bars. All right. Okay, so that's it. Not too bad. All right, so these are all my equations. All right, but one side note. Oftentimes, of course, I forgot F prime C is the compressive strength of the concrete. So compressive strength of concrete. Okay, compressive strength of concrete, of course. Okay, but one side note, oftentimes when I design my shear, I still have flexibility of adjusting ds. What if, not normally, right? You have folks coming in to design the flexure resistance first, right? And then you come in to do the shear. So at that time, you know the ds. But in the case that you don't know ds, we can always assume ds roughly equal to 80% of H. So this is one is not given. Make assumption, right? Make assumption, right? So that is clear. That is clear. Okay, so with that, you now know the concrete contribution, right? So going back to equation number 3, and let me label it. This is equation number 3. Okay, equation number 3, and I can bring this equation number 4 in equation number 3. So from equation 4 to equation 3, so plug 4 into 3. What you have is now Vs, shear resistance from steel, has to be greater than or equal to Vu divided by phi, which is 0.75. You know that already, minus 2 lambda square root of F prime C BW ds. Okay. So now all you have to do is find out the shear resistance from steel. Okay. Okay. All right. So now our job is to find shear resistance from the steel. So how to find the shear resistance from steel? We go back to the free body diagram, and we mentioned that what if I happen to have one stirrups sticking out, right? So naturally it will be AB FYT, where AB is the cross-section area, FYT is the yield strength of the bars. But you're not so lucky all the time, isn't it? Sometimes you just go natural, right? Not so lucky. So when that happens, you take a look at the section again in detail, say that, what if I still have the cut? I'm going to use the cut all over again and say that I have a free body diagram like that, and I have now a few more bars sticking out. Maybe one bar sticking out here. All right, another bar sticking out here. Okay, another one sticking out here, all coming out to play. All right, all come out to play. And let's just say that each bar, let's just say that each bar will have a cross-section area of AV. Okay, so this is AV. Okay, and this is AV. And this is AV. Okay, now each bar will give me a tensile resistance, and so let's call it small t. And this is a bit confusing because T usually is dimension, but let's just say that is T, okay? Each bar will have a shear resistance of T. Okay, so T now would equal to the cross-section area of stirrups AV and multiplied by the yield strength of the stirrups FYT. So this is the cross-section area of the stirrups. And this is the yield strength of the stirrups, I apologize, today's class is a little bit boring and dry, but these are the methodologies I just have to run through with you guys, okay? Run through with you guys. All right, so this is the tensile resistance for each stirrups, okay? Each stirrups. And where we added, right? Let's take a look at it. Now, FYT is the yield strength of the stirrup. Usually for our case, is given either 60 KSI or 40 KSI or whatever number we tell you, right? So that's not a hustle, we know that. But the real question is, what is my AV here? Okay, what is my AV here? Now I start looking at this, right? I see this is only a side view. This is only a side view. That means that if I look at isotropic view, the 3D view, what I really look at is this thing here, and try drawing a 3D drawing here, but this is my stirrups, right? This is my stirrups, okay? And now I have my stirrups going in the wrong way, apologize. Let me try to do this right. Okay, so how about I do this? Okay, and I copy it, and I paste it like that, and copy it, paste it like that. So there's 3 stirrups, right? 3 stirrups. Now, when I do the cut, right? Before I do a cut, let me draw the section out, right? So section looks like this. Section looks like this. Okay, and that is end of it. That is the side view. Okay, and this is the extension of that. Okay, let me just wipe this out so you have seen the section like that. And there's a dash line here going on like that, right? So that's the end of it, right? When I make the cut, folks, when I make the cut, right? So the 45 or this kind of diagonal cut truly are looking like this. So it cuts here, it cuts in here, and then it goes across three, right? Goes across 3 stirrups. So it goes across 3 stirrups. So that means when I do the cut, the stirrups, right, will be cut here, 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 here. All right. So now it means if I pick out the stirrups out, and this is the stirrups look like, when I do the cut, right? When I do the cut, what you see is a side view. What you see is a side view. What you see is a side view. But essentially, when I make the cut, I cut here. I also cut here. So it's actually 2 cuts. Or we call it 2 legs of stirrups, of each stirrup. Each stirrups. 2 legs, we cut 2 legs. All right, so if this is the case, when I calculate AV, that is the cross-sectional area, I need to calculate 2 legs. So if each leg gave me an area of AS, so AB equal to 2AS. Okay, now let's put this into practice, right? Into practice. So if I have number, so example, if I have number 3 stirrups, and usually stirrups are either number 3 or number 4. So number 3 bar size of stirrups, the AS for each leg should be 0.22 inch squared. If you don't remember this, go back to your table, you find this number, right? Find the number. And now for the shear calculation, AV is then 2 legs. So 2 multiply AS, that is equal to 0.44 inch squared. Okay, 0.44 inch squared. Okay, sorry, I think I made a boo-boo here. Okay, apologize. This is actually 11. Okay, and this is 0.22. Okay, check me, okay? Please verify.
Right, yeah, it should be 11.
Thank you. Okay, so that is how we calculate the area for stirrups. All right, so trick number 1. Now I draw it like this, so hopefully you see it. And let me just shade it, the cut, so you see that later on. My drawing is really horrible, but you get drift. But that is to say that each stirrups will have 2 legs exposed. Okay, and mind you that where we're at, we are looking at contribution from each leg, each stirrups, right? 2 legs, but each stirrup. So this is T, this is T, this is T. So across the section, right? How many T's I have? I have 3. But I know I have 3 because I put there 3, right? But how do you know it's 3? So how do you calculate that? This goes back to the original assumption. What is the original assumption? So take a look at this thing again, okay? Take a look at this thing again. Okay, and remember we said this is a 45-degree angle. So if it is 45-degree angle, and I'm going to just do this, right? I'm just going to do a line here. And I assume, dash line, draw out of the proportion. And I assume this is 45-degree angle, okay? Now I have this little bit compressive zone left. So it's kind of inverted section, okay? And I assume this is ds. Okay, I flipped it, I assume this is ds, then 45-degree angle gave you this little triangle here, right? 45 means this side equal to this side, so tangent 45 equal to ds over ds equal to 1. So tangent 45-degree equal to ds over ds equal to 1. So that means I have a crack length, and this is very important, folks, is that theoretical crack length. And when I say crack, it's really diagonal crack, okay? Diagonal crack. Okay, crack length is depth, ds. Diagonal crack length is ds. Okay, so that means if I have stirrups sticking out like this, I have 1 stirrups, 2 stirrups, 3 Mississippi, 4 Mississippi, am I counting sheep, right? But I don't know, right? Let's assume that I have a spacing between stirrups called S, uniformly distributed, okay? Every spacing S, I put the stirrups down, okay? I don't know how many stirrups I have in the section, how to calculate that. So the number of stirrups, so number of stirrups that have been exposed to the diagonal cut or diagonal crack, okay, is N. So N should equal to depth ds minus S. Okay, got it? So I have this length and divided by spacing, right? So I know how many stirrups I have in the cut. Okay. Now, why that is so important? Because if I know that, right, my total shear resistance from the steel at the diagonal cut is total shear from stirrups. Is then Vs equal to N times T. T is the shear resistance from each stirrup, right? So that is equal to N equal to ds over S multiplied by T AV Fy. And ladies and gentlemen, you finally have it. And that is the design equation. Oh, sorry. That is the design equation for stirrups. Okay. And ladies and gentlemen, you can find this equation from ACI code. And that is ACI 9.3.3. So ACI is going to put roughly 9.3 here. Okay. All right. So let's call it equation 5. Okay. All right. So I'm pretty much done. But today I will continue tomorrow with inclined stirrup. But today you know that for vertical, and note that all these are vertical stirrups. Okay. Vertical stirrups. Vertical stirrups, meaning the stirrups are straight. Okay. So vertical stirrups. Okay. So Vs has to be greater than equal than V over phi minus this. And Vs has to equal to AV Fyt multiplied ds over S. So this is all you need to know for shear design. Okay, and let's call it equation 6. The order is a little bit not right. Okay, this should be 5, and I should put this whole equation down here. I call it 6, but save my time, right? So just attach there and call it 6. Okay, all right. So that is the theory part for shear design. Okay. All right, so today is purely conceptual, and I apologize, it's very dry and very bony, but we have to gnaw this one off before we can move forward for real numbers. So please take a look at this and we'll continue on Wednesday. All right, if you have any questions, please stay behind. We can free to discuss, and I'll get back to you on Wednesday with all the details on the numbers. Okay, well, today is Wednesday, right? So sorry, next Monday then. Okay, other than that, have a great spring recess, and I see you after spring break, spring recess. All right, bye now. Jacob, you have a question or anything? Any question?